Okay, this is a recap on the topic of waves, sound and light. So there are two types of waves. We've got our longitudinal waves and we've got our transverse waves. So in a longitudinal wave, the actual definition is particles vibrate parallel to the direction of motion or the direction of propagation. So what that means is if you have a longitudinal wave, here it's pictured here, you're vibrating the particles back and forth and the wave is travelling then in that plane, okay, parallel to the direction of the motion. In transverse waves, this is one pictured here, you are propagating up and down and they're travelling perpendicularly to the direction of motion. They're travelling along the waves horizontally. So you can almost visualize that if you had a piece of string or a slinky and you moved it up and down, you would get these sorts of patterns, these waves. If you had a slinky and you moved it backwards and forwards, you would get this pattern. So this is the names of the components of the wave. So at the top of here, we've got a crest. At the bottom, we've got a trough. The point between 2 points, the distance between 2 points, such as the crest to a crest, is a wavelength. Similarly, a trough to a trough is a wavelength, or any point in the wave to the corresponding point in the wave would be one wavelength. It's the length of one wave. A wave goes from here to here. Okay. The amplitude is the height of the wave. Okay, so that pretending that this is the zero line, that is the amplitude. The zero line could be here, in which case this would be the amplitude. Okay, the wave equation is velocity is equal to frequency times the wavelength. Okay, frequency is measured in hertz, and hertz is given seconds to the -1 or 1 over seconds, and that comes from this equation where frequency is equal to 1 over time. Time being measured in seconds, so the measurement for frequency is 1 over seconds, which is seconds to the -1, which is equal to hertz. Wavelength can be measured in centimeters, meters, kilometers, any unit of length. For our purposes, we'll try to keep it in meters so that we can keep velocity in meters per second. Okay, so this is meters per second is equal to 1 over second times meters, which is meters per second. Okay, reflection. At a mirror or a barrier, an incident ray, pictured here, will reflect at the same angle. So the angle of incidence, which is the angle it makes with this line here, which we call the normal, is equal to the angle of reflection. Okay, so I equals R in reflection. In refraction, we don't have quite the same thing. We still do have reflection, but it's very weak. And we have a barrier here, so in this case we've got a more dense medium going to a less dense medium. Oh sorry, we've got the opposite, we've got a less dense medium going to a more dense medium, and because it's a more dense medium it travels slower and bends towards the normal. So here's our incident ray meeting at the normal, and the normal is 90 degrees to the barrier, and the barrier and then the wave, the refracted wave bends towards the normal. So the analogy I like to use for this is if you have 10 people in a row holding a pole, walking along grass, and then this barrier being mud. As soon as one person starts to walk in the mud, they will walk slower than the rest of the people. Okay, so then this person won't have travelled as far as this person, and therefore the wave will start to bend. Okay, and that is how refraction essentially works. It's just curving the wave fronts, for want of a better way of explanation. Okay, so sound waves. Using a cathode ray oscilloscope, which is just a thing that we use to convert sound into electrical energy. So we'll take a microphone, wire it up to this cathode ray oscilloscope, which will give us these diagrams. Okay. So here we've got a lower frequency diagram, and here we've got a higher frequency diagram. Okay, so here this low frequency diagram will have low pitch, and this higher frequency diagram will have higher pitch. Okay, and the difference between these two, if I can sort of select all of these, is they're the exact same frequency, so they're the exact same pitch. However, the amplitude of this one here is higher than the amplitude of this one. Okay, and because that's higher, it will be louder. Okay, so that's what amplitude symbolizes in a sound wave diagram. So we know that sound waves are longitudinal waves, and they don't actually take this waveform. The waveform that they actually take is the sort of compression and rarefaction side of things. Okay, but this is just a way of converting it into electrical energy so we can visualize it a bit better. So sound does reflect. If we think about us shouting in a room, you can hear the sound coming back to you as an echo. Okay, this is used in industry. If we have ultrasound and a ship is using it for sonar, it can detect rocks and things underneath it because ultrasound has a greater frequency. So ultrasound's anything over 20 kilohertz, so 20,000 hertz, so 20,000 points passing a second. And ultrasound is just hearing the reflections. So it's also used in industry with pregnant women, and you essentially just pass a detector and transmitter, and it transmits and detects at the same time. So it sends and receives the signal. So that is sound reflection. Okay, so mirrors, this complicated looking diagram here is just looking at something in the mirror. And this is what we see. It's a virtual image, and this is the image, this is the real object. So this real object emits light rays, as all objects do, and those light rays we see reflected back to us, okay? But what we see is their mirror image. So essentially, if we were to draw this just a little bit simpler, if we have our object and the eye, we see the reflection, but in reality what we see is a mirror of this object, okay? So that, if you follow the lines on each of the diagrams, you'll be able to see why that object looks the way it does, why it's inverted, okay? And it's just how mirrors work. Periscopes, on the other hand, are used to look over an object. If you picture, a submarine coming through, there's always a periscope with someone looking at the objects, because obviously you can't see out the front of a submarine. You have to look through the periscope. So looking through a periscope is just a way of using mirrors. These are mirrors to sort of bend the light to your will. The light's not actually bending, it's just reflecting. But you are able to then, see over objects. Dispersion. So here we've got Pink Floyd's Dark Side of the Moon album. Dispersion is just white light going through a block and then refracting. Okay, so this block is glass, and we have a medium going from a less dense to a more dense medium, and therefore it'll bend towards the normal. Now, white light is made up of our rainbow colours, so red, orange, yellow, green, blue, indigo, violet. Okay, violet is at the ultraviolet end of the electromagnetic spectrum, and red is at the infrared end of the electromagnetic spectrum. So if we go to our electromagnetic spectrum and skip on a little bit, we've got our ultraviolet has the higher frequency, and our infrared has the lower frequency. Okay, so the speed of these waves of these colors are different. Okay, so they're all together on the white light, and then we split it using our prism. So with this barrier we've got our incident, our normal, and then this moves away from the normal, and the higher frequency colors will move away from the normal more than the lower frequency colors do. Okay, so the lower frequency colors are your reds, oranges, and the higher frequencies are your violets and your blues. So the reason that rainbows happen is if we have a shower of rain and the white sunlight is coming through, that is dispersed into our rainbow. Okay, so that's why rainbows happen, it's just dispersion. Total internal reflection, on the other hand, is whenever you reflect light at a barrier. Now this, before your critical angle, this will refract, and it'll refract going from a more dense to less dense medium. It'll refract away from the normal, and if we go at a great enough angle, it will refract at 90 degrees to the normal. At 90 degrees to the normal, our angle at incidence is known as our critical angle, because beyond our critical angle, it totally internally reflects. Okay, there's no refraction. This is used in industry and fiber optics, where the light comes in at the barrier and it bounces along the fiber optic, and that is why we doesn't disperse, it doesn't refract, it doesn't go into the cladding. We don't lose any light, and we're able to bend light and use it to pass light through a distance without losing any of our light. So this fiber optics are used for your broadband, for example, your Wi-Fi signals. The electromagnetic waves are sent through the fiber optic, and they travel for miles and miles and miles, and you get a coherent signal at the end. Okay, so there are two types of lenses. You got your converging lens and you got your diverging lens. So converging lenses converge the lens towards a point. So they bring all the lenses together towards a point, okay? So this is used for nearsighted people to bring the lenses, bring the rays of light towards a point. This straight line doesn't look like it's converging, and that's only because it's passing through the optical center. Okay, and nothing through the optical center converges. It's the equivalent of drawing a line through the normal. A reflected ray through the normal will reflect along the same angle, and a refracted ray at the normal will not refract. Okay, you'll just get your wave fronts slowing down slightly, but it doesn't refract. Okay, so all of your rays, which will be passing parallel, will converge towards the same point. Okay, diverging rays our diverging lens does the opposite. Okay, it spreads the rays out as if they were coming from a point. So in this example, it's the point here. The rays all start off at parallel. The ray through the optical center does not deviate, and the other rays spread out and refract as if they came straight from a point, the focal point, which is behind the lens. Okay, so the electromagnetic spectrum, which I touched on briefly there, has going from long wavelength to shorter wavelengths, and in doing so it goes from low frequency to high frequency. Okay, so wavelength increases going this way and frequency increases going this way. So our high frequency low wavelengths are gamma rays, and our low frequency high wavelengths are radio waves. So going up in frequency, we've got microwaves. Then going up again in frequency, we've got infrared. Then our visible spectrum, which makes up this tiny portion here, from 400 nanometers to 700 nanometers in wavelength, or I think it's 4 times 10 to the 14 to 7 times 10 to the 14 in hertz, but don't quote me on that there, I need to double check that. Then goes to ultraviolet, then X-rays, then gamma rays. Okay, so what do these do? You can see here, so radio waves are used for communication, TV and FM radio. Microwaves we use for mobile phones, satellites, GPS and cooking. Infrared, all hot objects give off infrared radiation. We use it in night vision and remote controls. We can also use it for cooking. Visible light is used for sight and also photosynthesis of plants, and ultraviolet light is used for detecting forgeries, and it also gives you sunburn. So ultraviolet light is produced by any object that is over about 4,000 degrees Celsius. X-rays are used in medicine, and we can use them to both detect and treat injuries. Gamma rays are used in cancer treatment. They're also used for detecting leaks, and they are also used for killing surface bacteria in food in order to prolong the shelf life. Okay, some of these are quite dangerous. Microwaves, because you contain a lot of water, and the way that they cook is by the water molecules absorbing the microwaves and heating up. Then microwaves can be quite dangerous because we contain quite a lot of water and can heat up quite quickly with microwaves. Infrared is also dangerous because it comes off hot objects and can burn you. Visible light's not too dangerous unless you're looking at the sun too long, in which case you can go blind. If it's got a high enough intensity, you will go blind from visible light. Ultraviolet light can be quite dangerous because the sunburn that you're getting there is essentially damage to cells, and that can give you skin cancer eventually. X-rays can also damage your cells and give you cancer, and the same is true with gamma rays. That's my recap for the electromagnetic spectrum. Of course, we'll go over a lot of things in more detail. Alright, thank you.